All right. To finish off that introduction to dynamic data structures, there was one thing that I still had to show you for that previous chapter, and that was bringing it all together and using our linked list implementation, or our functions with which we can implement linked lists, together with dynamic memory allocation, to provide us with the new implementation of what we can now consider an abstract data type, a stack. In this case, a stack of integers. And this is the one slide which summarizes it all. But instead of going through this slide, let me just show you the actual program, which contains exactly what is on this slide. And I've got that here. Remember that this is the header file for the abstract data type stack that I wanted to define. It looks very similar to the one that we had for the abstract data object of a stack. The main difference is now that we define a stack as a pointer to an unspecified struct. And we can use the concept of a stack, the data type that is being defined here, as argument for all the different functions which we can use and define for the different operations that we typically have on a stack. Now you see the difference to the abstract data object. The abstract data object, there was only one stack, and then we were pushing and popping elements onto and off this particular one data object. Now here we have the possibility to create as many stacks as we want. And this is why, in particular, there's one function that says new stack, which returns a stack, which is a pointer to something that, as a client, I don't really care about how this is implemented. And then the stack can also be dropped. When the client says, I don't need the stack anymore, then when we implement the stack, have to free the linked list or the dynamic memory that has been allocated for this stack. And all the other standard functions, they now take stack as an additional argument. So when you as a client want to operate on a stack, you always have to tell these functions what stack do you want to use. This was our header file, and here's the implementation that now uses the idea of a linked list instead of a fixed size array for a stack. In particular, you can see here the definition of a node, just in the way we have defined nodes for linked lists. Then we define the actual stack wrap, the structure, which was undefined in the header file, but now for the implementation, we provide a concrete implementation that is encapsulated, so the user of that module can't see it. And all we do here is we keep track of the height of the stack with an integer, and we have a pointer to the beginning of the linked list, which I call top pointer. So the head of the linked list shall always be the top of the stack. And then we can go through the individual functions, now all implemented with the idea of a linked list to be used as a stack. In particular, the first function here creates a new stack by allocating enough space for this stack representation, which just requires an integer for the height of the stack, how many elements do we have, initialized to 0, and a pointer to the head of the linked list, initialized to null, because we don't have any element in the linked list. Now here we have a function that frees all the memory that is associated with a particular stack. And that consists of two tasks we have to do. We first of all have to remove all the elements in the linked list. That is, we have to free the space that has been used for all these elements. This we do with that while loop, which is similar to the free function, freeing all elements of a linked list that we looked at the very end of last week's lecture. This is one thing we have to do. This happens in the while loop. And in the end, we also have to free that stack wrap itself, which we malloced before to keep track of the height and the beginning of a linked list. That's removing, checking whether a stack is empty. This is really straightforward. We have that stack pointer, and if the height is 0, then the stack is empty. Inserting an element. Now, given that the top element is the head of the list, pushing an element onto a stack means we have to add a new node at the beginning of the linked list. So we use that same function that we looked at, which was adding an element to the head of the list. And this is what happens here. We allocate space for one new node. We fill that node with the data, with the value that we want to push onto the stack. And we say that the next element of the new top element of the stack is now the previous beginning of the list, so that it's really appended at the beginning of the list. And we say that the new top of the stack is the element that we've just created. Plus we say the height is incremented because we have one new element. Now, removing an element, that is popping an integer from the stack, first of all requires that the stack has at least one element. This is the assert here. And then we take out that element that is the current head of the list and remove it. Importantly, we, at this point, immediately free the memory that has been allocated by this one particular element. The height is decreased, and the top of the stack is now the successor in the linked list of the previous top. This is why we have S arrow top is S arrow top next, the next element in that linked list. And popping should return the actual data, the value that was on top of the stack, which is what this return D here does, where D is the head's data. Note that we cannot write return head data directly here because we've just freed that element head. And in principle, that means the memory is no longer available and might have already been overwritten. And that's all we have for this stack implementation. Just to show you an example of how that works, let's look at a program that you have written for one of the past homeworks, where the task was to use a stack, and in this case, for the homework, it was the abstract data object, that is the stack with only 10 elements, to convert a decimal integer into a binary integer. One of the problems with the implementation in the homework was that because the stack had space only for 10 integers, if you had a large enough number, then you would have caused what is known as a stack overflow. This can now no longer happen. We have almost as much memory as we need, and certainly for converting all possible integers that we want to convert. And the program here now uses the functions that are provided by the abstract data type. That is, we create a new stack. Then we run the algorithm by pushing elements onto that new stack. And while the stack is not empty, pop elements from the top of the stack. If you don't really understand what happens in this algorithm, then it means you haven't done the homework properly. And you should go back to that past homework and check that program and see how it works. And then appreciate the fact that it works much better with this abstract data object, this abstract data type, than with the abstract data object. I've written a makefile that uses this new stack implementation and the binary conversion program to construct a program called binary. I think there was one example that I had in the past homework, convert 1 to 7, using a stack to a binary number, and then this was the answer that you got. 1 to 8 would give you this binary number. All these bits are on the stack, so as soon as you have an integer that requires more than 10 bits, the old program would not have worked, so this wouldn't have worked, but now we can easily do it, and we can do that with all the integers that our system can process as an integer, and the size of the stack is no longer a problem. So that's what has happened here in that implementation of the stack with the help of a linked list and with the help of dynamic memory allocation. What is actually on that slide is exactly what you have seen in the program, or the implementations of all the functions that we had defined in the header. And that now really concludes the introduction to dynamic memory allocation. Just as a summary, how we do that in our programming language C. There are basically these two functions: memory allocation malloc, where the aim is to allocate memory for a particular data object. It always attempts to allocate a block of memory of the size that you provide as argument. It uses the heap for that purpose, which is the largest memory region in a C program. If allocation of memory is successful, it will return a pointer to an unspecified type, because you can use it for arbitrary types, to the beginning of the block. If there is insufficient space in the heap, and you can easily test that out and ask for 10 gigabytes or 100 gigabytes on your computer, then the system will probably say no. What you then get is a null pointer, and we know that we had better always check whether the allocation was really successful before we start using that memory region. Do note that we can't predict where an element will land. It really is random, and also we don't know what the initial contents of the memory block is. In particular, when we free memory and then we allocate memory for another element, we might just reuse space that has been used before. And there's still old values in that. So you would always want to make sure that you initialize the space that you have allocated properly. On the other hand, we have the function free, which is used for memory management to make sure that our program doesn't have what is known as memory leaks, occupied heap space that is no longer accessible and no longer needed. Free releases a block of memory that has been allocated by malloc, and you have to make sure that the address that you provide here as argument is the address of a block of memory that previously has been mallocked. And in this way, the system knows exactly how many bytes it has to free. If the pointer was not, if that address was not mallocked, then it is highly unpredictable what is going to happen. Do note that the contents of the memory block is not changed, just for the sake of efficiency. All the pointers to the block still exist. If you had a pointer that was pointing to some address in that memory block, then the pointer keeps its value and still has that address, but you should no longer access that memory through that pointer because it has been freed, and you don't know what happened with the memory. In particular, it may have been reused as soon as it has been freed. Right, I've mentioned that last week. Just a summary for this chapter. We looked at memory management, how to do that in C, but there are many other languages, unlike Python, that require us to handle memory ourselves for the sake of efficiencies. This is why programming languages like C tend to be much more efficient than programming languages like Python, which do a lot of work for you. We use that for dynamic data structures, and in particular we looked at linked lists that you should be very familiar with from 9.021 already, and seen how we can use that concept in C, and what we have to do if we have to manage memory ourselves. A few sections in the two books that deal with these issues that we looked at in this chapter. That means that we can now move on to the next chapter. As a matter of fact, we can now kind of close the introduction to the principles of data structures to this point, where in particular we looked at abstract data structures, encapsulation, the whole process around this, hiding information from clients, because we want to divide our programs, larger software projects, into modules. And we looked at dynamic memory allocation. And now we move on to the larger part of this course, which is going to deal with algorithms. And the first thing that we're going to look at is the analysis of algorithms, in particular their runtime behavior, before we start looking at specific algorithms for a variety of different problems. So that's what we will be looking at today, principles of algorithm analysis. This is mostly handled in the second chapter of Sedgwick's book. Do note, as I'm sure you all are aware of, the assignment deadline is in just a little over 6 days. Next Monday, 1 minute before midnight. I can see with the traffic on the forum that a lot of you have started working on the assignment. I also have received about a dozen submissions already. There were a few questions on the forum that kept repeating, which is why I would like everyone to encourage to look at the frequently asked questions before you post a new question on the forum, whether it might have been answered here. In particular, there were questions about one particular function and the question why it has memory, why it has pointer arguments. There is a hint here on that slide how you can find out why it has pointer arguments and how you're supposed to be using it. And there was a question also very specific for stage 3, what happens if a transaction on one of the transport cards takes you below or above the initially allowed minimum or maximum. This is perfectly okay. I say you don't have to check it. I just didn't want to make it too complicated. Just keep it as simple as possible because this wasn't the aim and the core of that assignment. Now, back to today's lecture. And before I'm going to start, there's another series that I want to start besides the advices from the Tao of Programming. I think this is also important for every computer scientist to know a few of the real famous computer scientists. So you will get to know a few of the nerds, which I think every serious computer scientist needs to know. Now, look at that photo and look at that person who's standing in the bus door. Does anyone recognize him? Turing, yes, excellent. This is Alan Turing. A few words on Alan Turing. He is by many people considered the founder of computer science as a scientific discipline. For example, the, as we like to call it, quote, Nobel Prize of Computing, the Turing Award, is named after him. There is no Nobel Prize for computer science. The Turing Award, just like the Fields Medal for mathematics, is considered the equivalent of a Nobel Prize, and it is named after Alan Turing. He studied maths and physics at Cambridge University. He invented in 1936 a mathematical theoretical concept, which is also now named after him, the so-called Turing machine, which is a framework for complexity theory, runtime behavior of algorithms, and computability, what can be computed in principle. It's very fitting to put Alan Turing for today's lecture because I will at least mention the Turing machine later today. We won't go into details, but if you are getting more serious about complexity, runtime analysis of algorithms, then you will have to learn about the Turing machine, that's for sure. During the Second World War, he worked as, this was a very practical application, of a form of engineering and computer science as a code breaker and was able to crack the Enigma code. Then after the Second World War, he designed early computers. He also published early papers on a variety of artificial intelligence topics, such as neural networks, foundations of programming, but also chess computers. This was one of his hobbies. And he was predicting that it would take a few decades before computers will be able to beat the best human players, and this has already happened in games like chess. It also has happened in Go, which proved to be more difficult, but now our programs are better than the best human Go players. The second very well-known concept named after him is the Turing test that he proposed in the 1950s to test whether a computer system can be said to be artificially intelligent. And lastly, this is rather sad, he committed suicide by biting into a poisoned apple in 1954 at a fairly young age. He would have most likely developed many more foundational theories for computer science if he hadn't committed suicide. Now, most of this I took from the biography, which is mentioned here. And if you're really interested in reading more about Alan Turing, I can highly recommend that biography. Fun fact on the side, there are people who believe if you see an Apple computer and you see that logo, that Apple, you would see that there is a chunk bitten off that apple, and several people have suggested that Apple used that logo in reference to that biting into a poisoned apple, but apparently this is an urban myth and is not true. Okay, now let's look at the analysis of algorithms, and let's come back to Turing and his machine a little later. As I'm sure you know, an algorithm, by definition, is a procedure, step by step, for solving a problem in a finite amount of time. Almost all algorithms that we know and we develop map some input to output, and almost all algorithms, when you run them, you will see that the running time typically grows with the input size. Now, the question that we always like to ask when we wonder whether an algorithm is really efficient or not is how much time does it take to run an algorithm? Very often, it is very difficult to determine the average time, and this is why the focus is usually on the worst case running time, trying to find out under the worst conditions, is that a good algorithm or not? Is that an efficient algorithm? What's the runtime behavior of this algorithm? Now, the focus on the worst case is because it's easier to analyze, and it's also very crucial to many applications, such as where time really matters, finance, robotics, or games, where you're really interested in, can you be sure that after a certain amount of time, a problem has been solved? So typically, when you look at the running time behavior of an algorithm, it might look like this. As you increase the input size from 1,000, let's say, just randomly chosen numbers, to 2,000, 3,000, 4,000, then both the best case as well as the average case and also the worst case, they typically go up. And in many examples, you have that in the best case, an algorithm runs faster than in the worst case, but there are also algorithms where the best, the average, and the worst case is exactly the same. But this is what you really typically have when you look at the runtime behavior of an algorithm. Now, there's, in principle, the possibility, if you want to know how efficient an algorithm is, to write an implementation that is a program of an algorithm, then run your implementation with inputs of varying size and also composition, maybe randomly generated input, and then measure the actual runtime and plot the result. This would be an experimental analysis or empirical analysis of your program. And what you might end up with is a plot of dots that you get here, where you have run different problems of the same input size and just plotted the actual runtime, which you can measure, for example, in milliseconds. And then the typical observation that you would make is that the larger the input gets, the longer it takes to execute that program. There are some limitations to the empirical analysis. First of all, it does require you to implement the algorithm. You can't look at the algorithm itself, the step-by-step procedure, but you really have to choose a programming language and have to implement it. This might be more difficult than an analysis of the algorithm itself, and then the decision that it will not be efficient anyway. The other problem is the results may not be indicative of running time on other inputs. Maybe you were really lucky with the 3 inputs that you chose, that it was very fast, but on average, or in the worst case, it will be much slower. And the other limitation is that you have to use the same hardware and the same operating system, and probably also the same programmer who knows a few programming tricks, if you want to compare 2 algorithms with each other. This is why in computer science we prefer a more mathematical, theoretical analysis of the runtime behavior of algorithms. And what we do, first of all, is we use high-level descriptions of algorithms instead of an actual implementation in a programming language like C. Now, these high-level descriptions of algorithms, they are also known as pseudocode, and we will use and see lots of pseudocode throughout the rest of this course here. At the beginning, the focus was on you learning the C programming language, but from now on, our focus will really be on pseudocode. That's one thing. Secondly, we characterize the running time as a function of the size of the input, and almost everywhere you will see that the input is measured with one particular number, n, which should take into account all possible inputs, and also will allow us to evaluate the speed, the efficiency of an algorithm independent of the hardware environment, whether I use a small laptop like this or a CSE lab computer, etc., and also independent of the software environment, whether I implement it in C or in Python, or whether I use a fast compiler or some slow interpreter. Now let's have a quick look at what I mean when I say pseudocode. This is how I will present pseudocode in this lecture. And this gives you a very simple example. It's a function that I call array max. The idea is to compute the maximum element in an array of integers. You can see I have input array A of n integers. This is really just using natural language English to explain what I mean. The output will be the maximum element in that array. And here's the actual algorithm. I use a variable current max initialized with the first element in the array. And then I've got a loop that loops through all the other elements with a conditional that says if I found an element that is greater than the current maximum, then the current maximum is set to that element. And I do that until the end of that loop, until I've inspected all the elements in the array, and I return current max. So that's obviously not C, and it's obviously not Python, but it's a description that you should be able to very straightforwardly implement in, for example, C. Now, what are the components of that pseudocode? Of course, there are different variations of the syntax, and everyone uses slightly different variations. There's no real standard for pseudocode. It is, however, a good idea to stick to a specific notation, and I will try to make sure that I, throughout this whole course, will stick to that notation that I'm introducing here. The first most important elements for pseudocode are control structures similar to those that you have in every language. We have conditionals and we have loops. If, then, else, and if would be the standard that I'm going to use. A while and while loop. I might also use repeat until. Just repeat all the steps until a condition is true. And for loops can be written in a variety of different ways. You can say for all, and then you say what you mean, or for each. We might say that as well. For example, for each node in a graph, we will do something, and so on. Functions I will declare in this way. A function has some arguments. I will also say what the input and the expected output of a function is. And then within these control structures, we can have expressions such as assignments, for which I will use the equality sign, we can, in conditionals and in while loops, do equality testing. And I will just also use that equality sign. A nice thing in pseudocode, you can easily do this, and there's no confusion to read this. What we can also use in pseudocode is superscripts and other mathematical formatting. It's not only allowed, it's actually really encouraged, because it's so much easier to read a mathematical, nice, compact description in a loop or in a statement rather than the actual C syntax that might be much more complicated. We will also sometimes use verbal descriptions of, and this is now really important, of simple operations that are really straightforward to implement. So for instance, I am perfectly allowed, and that makes a lot of sense in pseudocode, to say swap the two array elements AI and AJ. This is actually easier to read and understand than if you were to write the three program statements that would correspond to this. And whenever it is clear that everyone who reads that pseudocode would know immediately how to implement this, it is possible, legitimate, and even encouraged to use such high-level descriptions. Pseudocode is, on the one hand, more structured than English prose, as we can see, with those control structures, for example. On the other hand, it is less structured and less detailed than a program, so it lies somehow in between these two. It is, as I said, the preferred notation for describing algorithms in courses like this, in textbooks, but also when you work in a company, in a programming, in a team of programmers, and you want to describe specific algorithms to each other. You would not normally do that with the help of programming code, but with the help of something that does look like this pseudocode. The advantage is that it hides program design issues and focuses on the actual logic behind an algorithm. Let's have a quick look at one example. If you have diligently done the homework for last week, then you might have come up with this algorithm as an answer to one of the questions. At least this was my answer as a possible algorithm to solve a specific problem that was asked. And this is now really English prose that I'm describing here. It says, in the first phase, we iteratively pop all the elements from stack S and put them in queue Q. And then we dequeue the elements from Q and push them back onto S. So that's the first part of that algorithm. My question to you would be, now this is really English prose. How would you write this as an actual algorithm in pseudocode? Yeah. So let's look at that first paragraph. Now, imagine that you take pen and paper and you really have to write it down. While stack is not empty. While stack is not empty, pop. Pop and Q. You have to be a little more specific. You have to say what to pop, what to pop and what to Q. So just writing, it is perfectly correct to say while stack S is not empty, do, and then pop. Pop S, yeah. Yeah, so you want to say what to do with the element that it is the element that you pop from the stack, that this is the one that you enqueue in the queue. So you would say something like pop E of stack S and enqueue E into Q. Okay, so that's the first part. And then end while, this ends the first loop. How would you continue? So then we have dequeue the elements it should actually say the elements, all the elements from Q, and push them back onto S. So you would just naturally use a similar loop and say while Q is not empty, dq E from Q, and push E back onto S. What is the effect of this? The effect of this is that the elements now appear in reverse order on the stack. And this is what the first part of that algorithm should achieve. It takes all the elements on a stack and reverses them in order with the help of a queue. As a result, all the elements are now in reversed order on S. This is not something that you have to translate into a pseudocode. This is just an English observation. You might add this as a comment in the pseudocode, but you don't have to implement this. And then we have a second phase where we do the same thing again, but now we look for an element X. And that can also be translated into pseudocode. I have put it up here. There are different ways in which you can do this. The while loop condition is actually more formal than what you have suggested, because I don't know, it was you or you who suggested to say while S is not empty. And here I've said while not empty S, which is slightly more formal. But of course, you can also say while S is not empty, or while S still contains elements. All this is possible in pseudocode. And then the second part is I wanted to find an element now by doing exactly the same thing. And this has been done with the help of this variable found, a flag to be set false. If while I was popping and enqueuing elements, I found that X, then I just set this found to be true. And this is how you would, in principle, translate this English description that we just saw into something which is not like the C program that you could also now implement, but more formal than the English description. Let's look at another exercise. Here the question is, suppose you're given pseudocode, and now your task is to write an actual implementation for pseudocode. And the general rule is pseudocode should always be written in such a way that everyone who is supposed to read the pseudocode is able to do this. Take that description and translate it into a programming language. So let's look at this example here. Does anyone have a suggestion on how to, when you see swap the two array elements AI and AJ, how to translate this into C? And I'm just writing what you're saying. Yep, temp equals AI. Yep, so we can't really say sub I, we really have to say I. This is now C, and indeed, if T has not been declared, we have to make sure that this is an integer. And yeah, AJ equals AI, and AI equals Are you sure? AI equals AJ, and then AJ equals temp. So make sure that you don't overwrite what you haven't saved in your variable temp. Yep, so very good. This is the first example, and you can see it's pretty straightforward to translate that into C. Now, here's another example. Suppose that we have a pointer head to point to the beginning of a linked list, and the pseudocode says something quite similar to this, swapping these two elements AI and AJ. It says swap the head and the next element in the list. So you have a long linked list, and we just want to swap the first and the second element. Any idea? Yes, we need an extra pointer, just like the temp here. Say we use the same definition of a node of a linked list, the node type T, and we have a pointer which you want to call maybe temp, or might be easier if we call it successor, because that makes it clearer what we mean. Yeah, I think this is why I called it successor, because I wanted it to store the second element. But of course, your approach might work as well. It's just the one that I have in mind is indeed you store the second element in the successor. But I'm sure that there's, of course, other ways to do it. But let's do it in this way. So head next. And
head.net is equal to head.net.net.
all right, now we have a pointer, so we have to use the arrow. And now you say head next.
Head next is equal to head next next.
All right, of course you could have written successor here, because we've just set this to head next, but yeah. And
a successor's next is head, and head is equal to successor.
successor next equals head, and
head is equal to successor.
are we all happy with that? It might be a good idea to see if that really works. Suppose we have that linked list. We have head points to the start. Now, first step. So then successor points to here. Then head next is this address. Oh no, the next, well, this pointer here is redirected to this pointer. Okay. Then successor next is pointing to head. And then you say head now points to successor. I'm not sure why this is not really focused. Or is it just me? Much better. So head now points to this element. The pointer is gone and points to this element, and this points to this element. So this is exactly what we wanted to achieve. Yep, very good. Last question. Suppose we have a stack, and the pseudocode now says swap the top two elements on S. Anyone? Of course, we can use the standard stack operations. You pop the first element, store it in I, pop the second element, store it in J, and then push I and then J, and then you have reversed them. Yep, so very good. This is exactly what you have to do. Let me see if that is exactly what we had on our, yep, so that was my idea as well, except that indeed I've used successor here directly. But this is exactly the pseudocode that you came up with. Here we have the stack pop and stack push. You always have to be careful, however, with the pseudocode, that you really make sure that what you describe is easy to implement. If you look at this pseudocode, which is very similar to all the things that we looked at, but says swap the two elements at the front of the queue. Q. Why is that problematic?
Do you mean the first two elements in the array, or the first two elements to be dequeued?
Yeah, so all you have is the standard queuing operations. And the task is just like with the stack, where we wanted to swap the elements on top of the stack. We now have two elements in the front of the queue, and we want to swap them. And why is that problematic? When you dequeue, you would actually dequeue from the front. But when you then enqueue, they would end at the end of the queue. And this is perfectly right. So you can't easily implement this. So unlike this, which is straightforward, and you know exactly how long it will take, if you really want to do this, then you have to dequeue all the elements in the queue and have to enqueue them again. And that is not a simple operation. In particular, it might depend on the length of the queue, how long it takes to do that. And therefore, you have to be careful with a statement like this is not a good idea in pseudocode. Whenever you have anything in pseudocode, make sure that it is either easy to implement directly, or, this is perfectly possible as well, that you use a function that has been explained elsewhere earlier. We will do that with pseudocode a lot as well. We will define a few operations. For example, we have defined operations for pushing and popping elements onto and off a stack. And then we can use them in pseudocode, but only after we've defined them. Right, so much about pseudocode. Now let's get back to our actual question. How can we investigate the runtime behavior of algorithms? Now we are going to use what is known as the random access machine model, the RAM model, which in the very simple form consists of a central processing unit. It consists of a potentially unbounded bank of memory cells. We've talked about memory a lot already, each of which in the abstract model can hold an arbitrary number or a character, for instance. And we assume that memory cells are numbered and that accessing any of the memory cells takes the CPU some time. When we use that model, then to investigate our prediction for the runtime behavior of an algorithm, we then look at what we can consider primitive operations, which are the basic computations performed by an algorithm. These basic operations should be identifiable in the pseudocode, and they are largely independent of the programming language. Of course, how long they take will depend on your processor and on your actual programming language, but to just identify the primitive operations themselves is independent of any implementation. What's also nice and makes life much easier is that the exact definition of what counts as one primitive operation is not so important if we are only interested in the runtime behavior, the general runtime behavior of a program. And we will shortly see why that is the case. For these primitive operations, we assume that they take a constant amount of time in the RAM model. Now here are examples of what people typically consider as primitive operations in pseudocode. It would be evaluating an expression, such as a mathematical expression, a summation of two values, for instance, or a condition in a while loop. Indexing into an array is considered a primitive operation because you have to find the memory cell where a particular index points to. And also calling a function and returning a function is considered a primitive operation. At least for my purpose, this is what I want to consider primitive operations. As I said, the exact definition is not important, but it might be helpful if we look at some examples to agree on a very specific definition of what we mean by primitive operation. When we know what we want to count as primitive operations, then we can actually look into our pseudocode and start counting. How many primitive operations are required? What we typically do is not count the exact number, because the exact number of primitive operations might depend on the structure of the input. Sometimes we have to go into an if statement, and for other input we don't. So what one typically does, in view of determining the runtime behavior in the worst case, is to determine the maximum number of primitive operations. And one also does this as function of the input size, so that we get a more general result, and not only one for, suppose the input consists of exactly 10 integers. Let's see what we will end up with if we look at that very simple algorithm that I used to illustrate pseudocode in general, namely finding the maximum in an array of integers. This was the algorithm, and in particular we have said the input consists of an array of n integers, and I now want to count how many primitive operations are needed to execute this algorithm based on n, the number of integers that I get. Now I've added the numbers here. Let me explain where they come from. First of all, there is that one indexing into the array, A0, to access that first element of that array. That counts as one primitive operation according to my definition. Then I've got that for loop, which says for all I from 1 to n minus 1. And here I claim this requires n plus n minus 1 primitive operations. Now, why is that the case? Remember that primitive operations were evaluating expressions. And whenever you execute one round of that loop, there are, well, at the beginning, there's one expression you have to evaluate. Namely, you have to check whether your running variable has not yet reached the end. So if I has a specific value, every time before we can even start this for loop, we have to check whether I is small or equal to n minus 1. This is one expression that we have to evaluate, or I count this as one expression. And the other expression we have to evaluate is at the end of this for loop. We have to take our running variable I, and we have to increment it. So this is hidden here, but we can imagine that at the end of this for loop, here there's always a statement that says I equals I plus 1. You have to increment I. Now, we have exactly n minus 1 repetitions of this loop. So we have to execute the statement I equals I plus 1 exactly n minus 1 times. And we have to check whether I has not reached the end of the loop exactly n times. We have to do that one after we've done the last n minus first increment of I one last time to check that now we have reached the end of that loop. So this loop has, according to my definition, n plus n minus 1 primitive operations that are being executed. What do we have here? Well, first of all, we see that the statement inside of this loop has to be, in total, every statement has to be executed n minus 1 times, because this is the number of iterations through that loop. Here, in this condition, we see there are always exactly two expressions, or two primitive operations. One is to index into that array, and the other expression then is to evaluate the expression whether this element is greater than current max. So there's always two, and we have to do that n minus 1 times. So in total, there's 2 times n minus 1 primitive operations. And lastly, here we have only that indexing into the array, which is one operation. In the worst case, we have to do that n minus 1 times. In the best case, we don't have to do that at all. In the best case, we never enter into this condition. But we wanted to count the maximum number of primitive operations, and that means that in the worst case, our array is sorted, and every time we have to enter that condition. So that's what one typically does, counting these primitive operations. Always assume the worst case and just count what could happen. Lastly, we have that return statement, and I said returning from a function shall also count as one primitive operation. And then if you add all this up, you will see that in total we have 5 times n minus 2 primitive operations. Now that was really a bit painful and was using the exact definition of primitive operations to arrive at that number. And the question is, what can we now? Yes?
Just a question with that last slide. Your first line, n plus n minus 1. You're starting at index number 1, so would it be n minus 2 then?
So this is including n minus 1. Yes, so I have n elements, and if I were to start from 0 to n minus 1, it would be n. But since I'm starting at 1, it's only n minus 1. Does that answer the question? Yep. The assignment itself is not a primitive operation, just according to my definition. There could be other that define assignment as another primitive operation. The reason why this is typically faster is that a variable like current max could be used in a register in the processor, and then the assignment is faster than accessing into array. And this is why often this is not counted. But really don't get too focused on this specific definition, because as I said earlier, whether you count this extra or not will in the end make no difference. It's just if I specify exactly what I count as primitive operations, then this is what we would end up with. So with my definition of primitive operations, we see that array max requires 5n minus 2 primitive operations in the worst case. The best case requires only 4 times n minus 1 operations, and that is what I've already said. If you never have to go into the if loop, then you avoid the n minus 1 operations inside the if, not if loop, if condition, and this is why in the best case you've got 4n minus 1. Now the next question is, what does that tell us? We have now counted a few different things as primitive operations, and we don't really know how much time each primitive operation actually takes. But what we can say is that we just define a constant a as the actual time it takes the fastest primitive operation to execute, and b the time it takes the slowest primitive operation to execute. What we can then say is that if by t of n we denote the worst case time that it actually takes the algorithm to execute, then it must lie between these two bounds. If all the primitive operations take at least a and at most b time to execute, then my actual time lies in between these two boundaries. And what we can then say is that the running time Tn is bound by two what we call linear functions. Why linear functions? Because the size of the input n occurs as a linear factor here. And that helps us predicting that our algorithm, when we double the size of the input, roughly will double, it will take twice the time to execute. And if we increase the input size by a factor of 10, then we can expect the runtime to also increase by a factor of 10. This is what we typically have with so-called linear functions that provide bounds for the actual runtime of the algorithm. If you have seen that before, a type of runtime analysis, then you will know that these are probably the most commonly encountered functions that you will end up with when you look at algorithms and analyze their complexity. The best case is you have a constant algorithm, which just doesn't take longer, even if the input grows and grows. Logarithmic is also very good. We will see one example of a logarithmic algorithm. Linear is what we have just seen. If you increase this input size by a factor of 10, then the runtime would increase by a factor of 10. This is fairly special, but occurs in a variety of practical algorithms, such as sorting algorithms, efficient sorting algorithms. They would have this complexity, known as n log n, which is slower than linear, but faster than what is known as quadratic. Quadratic would be if your algorithm, and we will see examples of that as well, would be bound by two quadratic functions. And that would have the effect, if you increase the input side by a factor of 10, the running time will be increased by a factor of 10 to the power of 2, namely 100. And this is much, much slower than increasing the runtime just by a factor of 10 as well. Cubic is even slower. We will see also an example of a cubic algorithm. And what is typically the worst case is when you have an algorithm that has exponential runtime, 2 to the power of n. If you add only one element to the input, then that causes a doubling in the runtime. And that typically means that you can't compute solutions for reasonably large input. And we will also see an example of an algorithm later today that has this exponential runtime behavior. If we want to compare these different possible results that we can get from a complexity analysis, then a so-called log-log chart provides us a very good idea of the growth of a function. What's a log-log chart? It means that we have a logarithmic scale on both axes. Here we start at e plus 0 is the mathematical notation for this is 1, this is 100, this is 10 to the power of 4, which is 10,000. So you see a logarithmic scale here, and the runtime is also depicted in a logarithmic scale. Now that allows us to plot the three functions that we saw on the previous slide. This would be a linear function, and you can see that the runtime here is depicted as the same as the size of the input. Here we see a quadratic function. If this is 10 to the power of 8, then the runtime goes up to 10 to the power of 16. And this would be cubic. 10 to the power of 8 translates into 10 to the power of 24. Now these graphs you can easily compare. You can see that on this log-log chart, a linear function grows much more slowly than a quadratic function, which in turn grows more slowly than a cubic function. And one interesting aspect that we can see with these log-log charts is that the growth rate will not be affected by constant factors or by lower order terms. What do I mean by lower order terms? If, for instance, we have a quadratic function, 10 to the power of 5 is a constant factor times n squared, and we have a very, very large linear factor within that function, then that linear factor or part of that function actually does not affect the growth rate of that function, which is quadratic because of that higher order term that we have in here. And you can see that here, this yellow line is the standard linear that we had on the previous slide, and that dotted yellow line corresponds to that linear function here with that very high lower order term, 10 to the power of 5. This is why for very low input you already have 10 to the power of 5 as part of the runtime, contributing to the runtime. and we have that constant factor 10 to the power of 2. But you can see that although at the beginning the difference is fairly drastic, towards the end, when you look at further increasing the input size, the growth rate is actually exactly the same in both yellow lines. And you have the same observation with that dotted red line, which corresponds to this function here, with that large constant factor 10 to the power of 5, and that lower order factor 10 to the power of 8, which is very, very large, but it's a lower order. And again, you can see in the long run, this function grows exactly as the standard quadratic function. And that, in fact, is the secret why it doesn't really matter that much how you count primitive operations, whether you count assignments as part of it or you don't. When you look at the overall runtime behavior, since these constant factors don't really matter, it tends to make no difference in terms of how a function actually grows. Also, changing the hardware or software environment, because it affects Tn by a constant factor only. If you, instead of using this small laptop here, would use a much more powerful laptop, then it might be 100 times faster, or it might be 1,000 times faster, but still, this is only a constant factor. And it would not materially affect the runtime behavior of any algorithm as the input size increases. It really does not alter the growth rate of Tn. And this is why we can say that the linear growth rate of the running time Tn that we have determined for our algorithm array max is an intrinsic property of the algorithm, independent of any implementation and independent of any hardware or software that you are using. And I think before, well, let's see that we can do this exercise first, and then I'll have a break before we make all this even more formal, and I introduce the concept of big O as the notation for the runtime analysis. So look at this exercise here. We have an algorithm that computes the matrix product for two square matrices. The input is an n by n matrix, or two n by n matrices AB, and the output should be the matrix product, which you remember means to take one row in one matrix and one column in the other matrix and do all the pairwise multiplications and sum up all the result to get to the resulting element ij within the matrix that you want to compute. And this matrix is then being returned. So the standard algorithm is this. You have a for loop where you loop through all the rows of the first matrix. And you loop for of the resulting matrix. And you have an inner loop which loops through all the columns of the resulting matrix. And then you have a third inner loop that goes through all the rows of the ith column in A, and the jth in B, you go through all the, so here you go through all the columns of I in that row, and here you go through all the rows of that column in B in order to compute that element ij in the resulting matrix. Now let's count the number of primitive operations. And once we've done that, I will have a break. So here is the algorithm. And I would like to hear from you when we use the same definition of primitive operations, how much time it would take to execute every single line in that algorithm. Let's start with that for loop here. How many primitive operations would we need? n plus 1. So that's 2n plus 1. Yep, so as usual, counting the comparison to determine whether we have reached the end of the loop, as one primitive operation, which we have to do n plus 1 times, and the increment of the index variable at the end of every loop, we have to do that exactly n times. Then this inner loop. Anyone? Yes, that's exactly right. So we have the same looping through n elements. So that would be 2n plus 1. And we have to do that exactly n times. We have to execute the inner loop n times, because this is what the outer loop says. And the inner loop itself takes 2n plus 1. Cij equals 0. How often do we have to do that? N square, yes. We have to do that exactly n square times, because we have the outer loop n times, and n times n, we have to do the inner loop, and therefore n square times we have to do that. Okay, so that then means we have to do that. How often? N square times 2n plus 1, as usual, for our loop. And last question. What is the number of primitive operations here? Let me tell you that the way I count it is we have to access into this array, and into this array, which is 3. And 2 operations plus and times. It really doesn't matter, but if you count them as separate, then it would be 5 operations for that one single statement. And how often do we have to execute that statement? N cubed, yes, n cubed, because we have now 3 nested loops. N cubed. Anything else? And 1 for that return statement. All right, so if you sum that all up, then let me not do that in paper. Let me show you the result here, which says that in total we have, oh, this is what the result that you would get. You can verify that this is really what you obtain here. The main factor, and this is what determines the actual runtime behavior of this algorithm, is the 2 times n square and 5 times n cube. So we have 2 cases where we have a cubic number of steps that we have to execute. And this gives our total runtime here. That brings us then, and now it's really time to have a break until, let's say, 7:25. And then we will look at the formal definition of big O. All right. Time to continue. Yes. So, a question that I got during the break. Why 5 here? And I explained that this is just how I counted it. Indexing into an array, indexing into an array, and indexing into an array 3 times. And then this multiplication and the addition was counted as a separate operation. It really doesn't make much of a difference. If you were to count this as one expression, then you would have ended up with 4 times n cubed, and the result would have been 6 times n cubed. As we've seen, constant factors don't matter when we look at the runtime, and it really only depends on that specific definition of a primitive operation that I have here. Rest assured that it doesn't make sense to have an exam question that asks you to count primitive operations. And this is just to show you that depending on the definition that you use, you might get slightly different results, but the order of growth will not be affected by the choice of primitive, what you count as primitive operations. And this is what we will be looking at now when we introduce what is known as big O, the notation that we computer scientists use in order to write down the complexity, the runtime behavior of an algorithm. Here's the mathematical definition. I suspect that some of you have seen that, for example, in Comp 9020. For those, it will just be a nice repetition. The big O notation says that given that we have 2 functions that depend on n, f and g, we say that fn is OGN, which means the growth rate of n is bound by Gn. If the following is true, there are positive constants c and n0, so that with a certain size of input, and from there on, it will always be the case that fn is bound by Gn. Not directly bound by Gn, but by a constant factor. Let's have a look at a very simple example, and let's use the log-log scale, the log-log graph to illustrate what I mean by this. It really is on the log-log scale very easy and nice to visualize the fact that the function is bound. Here we have a function 2 times n plus 10, and the claim is this is On. It's a linear function. It is bound by just the simple function n. If we translate that into the definition that we just had, then it says that we have to find a constant c, so that our function 2n plus 10 is always smaller or equal to constant c times n, the function that we used as our bound, for all the n's from a certain n0 on. Now we can use some very simple mathematical rewriting to determine what we can use for c and n0 to prove that this is actually the case. If that is the case, then c minus 2 divided by n must be greater or equal to 10. So I'm just moving that 2n to the other side, and then divided by c minus 2 on both sides. So here you see that the result says n must be greater or equal to 10 divided by c minus 2. Can you then find a constant that satisfies this equation? 2 constants, n0, from where on n would satisfy this, and a constant c, so that this is true. An easy choice is to say pick c equals 3 and pick n0 equals 10. If you say that you use the constant factor 3, which is 1 more than the constant factor that we have here, this is why this is such a natural choice, then we just have to determine which n0 we need, so that this is really greater than this. And since here we have the constant factor 10, the natural boundary would be the 10 here as well. And you can see that for 10, the result is 30, and this is smaller or equal to 3 times 10, 30. And if n is greater than 10, then you will always have that this left-hand side is smaller or equal to the right-hand side. Now we can see that here in the growth scale, this line below is our function g, this function n. And we want to say that our actual function is bound by this function, modulo a constant factor, and that is important. Now, our actual function would be this here, this slightly curved function 2n plus 10. And it is curved simply because we have the log-log scale. Now, you see that 2n plus 10 is obviously always greater than n. But if we shift n slightly upwards, which we can do with the constant factor 3, then we get the dotted line here, which is parallel to that line. It has the exact same order of growth. It just uses that constant factor 3. And you can see that this is not a bound for this function in all cases, but from a certain point on, and it happens to be that intersecting point 10 here, from that point on, 3n, the dotted line, will always be greater or equal to our actual function 2n plus 10. And this is exactly the statement that we want to make with our big O notation. When we say f of n is OG of n, then we actually mean that we can take g of n, move it up, so that from a certain point on, our fn is always smaller or equal to the constant factor times gn. And that illustrates the relation between that formal definition here and the graph that illustrates what that function or what that condition amounts to, namely that in the long run, the function f of n will always be smaller or equal to the function g. Now here's another example. Suppose that you have another function that measures the runtime of your algorithm, n square. And now we want to see whether n square is maybe bound by also a linear function n. No, this can never be the case. You can see that graphically. This would be n, the function that you have here, and this would be n square. This is the growth, quadratic growth. Now, no matter how far you push this linear function upward by a constant factor, you can shift it upward so that for a good number of arguments, it is actually larger than your n square. But at some point, your n square function will outgrow the, in this case, 10 times linear. And also, if you use 100 times linear, then at this point, your n square function will outgrow the linear function multiplied by a constant factor. And in fact, no matter what constant factor you use, in the long run, your n square function will grow faster. We can also see that mathematically. Can we find a constant c, though, so that from a certain point n0 onwards, n square is always smaller or equal to cn? No, we can't, because that would mean that n must be smaller or equal to c. And we can't find a constant where this is the case. C really has to be a constant, and n, then for all n, it should be smaller or equal to c, and this is impossible. So n square is not bound by linear, and therefore grows faster. A few exercises where we can look at applying that mathematical definition. If you want to show that this function 7n minus 2 is a linear function, what constant c and what constant n0 could you use? What would be a natural choice for a constant so that 7n minus 2 is smaller than c times n? 8. You could choose 8. You can even choose 7 because we are actually subtracting something from 7. But 8 would work just as well. So indeed, we have that 7n minus 2 is always smaller or equal to 8 times n. If you want to show that this function is cubic, what constant would you use for c? 4, yes. So 3 times n cubed plus all these factors is not smaller or equal to 4 times n cubed for every n. Like if you choose n to be 1, then you have to add 20 here, 25, and that's 28, whereas 4 times n to the power of 3 would only be 4 for the case of n. But as n grows larger, and we can actually calculate exactly from which n0 onwards, as this grows larger, we will have that this function is always smaller or equal to 4 times n cubed. And similarly for this log function, we can also use a constant. Let me just show you which can be used here. Here we have, I chose 7, you could have chosen 8, obviously. Here we all have chosen 4, and then we can compute that if n is greater or equal to 21, then this will always be the case that our actual function is smaller than 4 times n cubed. And here for that log function, we can use the constant 8 times log n, and n0 equals 2. Now, this big O gives an upper bound on the growth rate of a function, as I've said. So when we say fn is ogn, then that means the growth rate, yes? Yes. So if a function is bound by n, then it will also be bound by n squared. I will say more about this a little later. But it is true, the definition, and did I have that? I think I might have, this might even follow from that table here. Indeed, this gives the first answer to that question. Fn is ogn means that the growth rate is no more than the growth rate of gn, but it can mean that it is less than the growth rate of gn. So as you said, if you have a function 2 times n, then this is also on squared. And you can see that from the table here. If, suppose, gn grows faster than fn, we have that fn is ogn. Gn grows faster, and therefore fn is bound by gn. Gn is ofn. No, this is not the case. If gn grows faster, then gn is not bound by fn. If fn grows faster, then it's the other way around. And if the two functions are of the same order of growth, then we have a symmetric relation. Fn is ogn, and gn is ofn. If we can determine that the runtime behavior of an algorithm is exactly bound by a function that has the exact same order of growth, then it's always advisable to use the smallest. So in theory, mathematically speaking, it is the case that the runtime behavior of our array max algorithm is bound by on squared. But we know that it is also bound by on. So the correct answer when we ask what is the question, what is the runtime behavior of that algorithm would be on, because that is the smallest function of which we know that the growth or our algorithmic, the behavior, the runtime behavior of our algorithm is bound by that function. A few big O rules that, again, some of you might have seen, but certainly not everyone. If we have that fn is a polynomial of degree d, such as 2 times n cubed plus 20 n squared plus 5n, then it's always the highest degree that determines the complexity. F of n is bound by O n d. Lower terms can be ignored, and constant factors can be ignored. And that can be very easily proved mathematically based on the definition. Here is now the answer to that question that you raised. You should always use the smallest possible class of functions. Although it is mathematically true that 2n, the function, a linear function, is not only on, but also on squared. The correct answer, when you want to say what is the algorithm, the runtime behavior of your algorithm, then you would say on instead of on squared. Also, you should use the simplest expression in the class. You could say, mathematically it is true, that 3n plus 5 is O3n, because 3n plus 5 is bound by 3n, but it would certainly be simpler to just say it is on. Actually, it's the same class, O3n and on, and the general rule is to always use the simplest expression. Suppose that your algorithm, when you count the primitive operations, would be determined, the number of primitive operations, by summing up all the numbers from 1 to the size of the input, n. Do you have a simple argument why this is bound by n squared? Yes, yep.
Sum of n numbers gives you n to the bracket n plus 1 by 2.
Yes, that's right. So I hope everyone knows how to compute that sum. It is, if you sum up all the numbers from 1 to n, a simple formula, n times n minus 1 divided by 2. And if you compute that, then it has that quadratic factor that gives you n squared plus n divided by 2. And this is obviously on squared. This is not uncommon to have an algorithm that has exactly that type of, or that number of primitive operations. If you have 2 nested loops, and the second loop starts at the index of the first loop, then you typically have a runtime of the number of primitive operations that corresponds to n plus n minus 1 plus n minus 2 plus n minus 3, because the inner loop will be executed fewer and fewer times as you go through the outer loop. But still, the overall runtime behavior, as we can see here, is on squared, as if the 2 nested loops were both running from 1 to n. So this is what is known by the asymptotic analysis of algorithms, which determines the running time with the help of that big O notation. And what you have to do for this purpose is you go through your algorithm, as we have done with our 2 or 3 examples, find the worst case number of primitive operations as a function of the input size, and then express this function using the big O notation. So you have determined your function, which could have been, what was it, 7 to the power of n, 7 times n to the power of 3, etc., etc. And we know this is on cubed. Or here, the algorithm array max, where we said it executes at most 5n minus 2 primitive operations. Then we would say algorithm array max runs in on time, in linear time. And you can really see with that example also that it doesn't make a difference what you count as primitive operations, whether this is 4n or 6n, and whether you have -2 or +3. The answer would always be this algorithm, and this is the intrinsic property of that algorithm, runs in O(n) time. This is why constant factors and lower order terms, because they are eventually dropped, can be disregarded when you count primitive operations themselves. And that makes life much, much easier, as we will see with yet another example. Now, this example, here the task is to compute the ith prefix average of a given array of integers. Now, the ith prefix average is defined as taking the first I elements in your array and compute the average of those first numbers. You can see that that happens here. The red bars, they indicate the numbers in your original array, and these bars for in X and these for A, that denote the average of the first I numbers. Obviously, it's the same for the first number. The average of a number itself is the number. The average of the first two numbers obviously lies somewhere between these two numbers. And then this number here is the average of the first three numbers. This is the average of the first four numbers, and so on. So now our task is to write an algorithm that computes the prefix average for all these elements here. There is important applications of these prefix averages, in particular in financial analysis, where I'm not sure if you have seen that, but if people look at development of stock market prices in order to investigate the actual trend of the stock price, and people typically use a window and say this is the 30-day moving average or the 180-day moving average. And that means exactly that. You take the first elements in the past and then compute the average over that element, over those elements, and then you compute a curve for those moving averages. And people seem to be thinking that with the help of these curves, you can predict the future development of stock prices. So they always compute these prefix averages. And we are now looking at two possible algorithms for implementing the computation of these prefix averages and determine the runtime behavior of these algorithms. Here's the first one, where you do a straightforward implementation. For every element in the array, you go through the elements in that array up to that index, sum them all up, and divide it by the number of elements. So you would, first of all, just take this number and compute this number. In the second step, you would take this number and add it to this number to compute this average. In the third step, you would take all these three numbers, sum them up, divide this by 3, and so on. And this is what happens here. So for all indices, you take the first element in your array, and then you add to it all the other elements up to the index I. That gives you the sum of all the elements up to that I. And then you divide this by the number of elements, which is I plus 1, since we always start at 0. And that gives you the ith average. Now we see we have two nested loops, which typically means that we have a quadratic algorithm. And we can actually see why this is the case. Now, using the idea that since constant factors are ignored in the end anyway, we make our life much, much easier. And instead of saying that we have exactly 5 primitive operations, we just say what is the order of the number of primitive operations that we have to execute. Now, here we have that loop that we have to do roughly n times. So instead of saying what we would have said, n times n plus 1 primitive operations, we now just say this is O(n). And clearly, this is much easier. Then we have to execute this statement, obviously, roughly n times, because that's inside of that loop. then we've got that inner loop here. And instead of now saying n times n plus 1, n times n plus 1, we just say n square, roughly. Since this is inside of these two nested loops, this operation is, we have to do roughly n squared times. And then we get outside of that inner loop, so that dividing the resulting sum by the number of elements to get the actual average, we have to do in the order of n times. And then just one operation at the end, a constant operation, is to return the resulting array. Now we can sum up these expressions here in the same way we have summed up the formulas that were actually counting the actual number of primitive operations. And we see we have 2 times on squared, 3 times on, and one constant factor. We can ignore this constant factor here. We can ignore all the lower order terms. And we see that the complexity of this is n squared. So we have a squared algorithm or a quadratic algorithm for prefix averages. Now this is one way to compute it. There is a smarter way of doing this. And this would be this algorithm here, where instead of recomputing the average for every index by going back through all the past elements again and again, you keep just a running sum that always maintains the sum of all past elements. And you can reuse that sum for the next computation without having to sum up all these elements. I assume that some of you might have already seen that when you saw the earlier algorithm and might have thought that this is not the most efficient way to do this. And indeed, this is much faster here, as we can see from our complexity analysis. So here we keep that running sum, which we initialize with 0. And then we have only one loop that is needed. We always take our array, current array element, add it to the running sum, and then we have to divide the running sum by the number of elements that we have summed up to a certain point. And that would mean, if we go back to our diagram here, that instead of, when we get to this point, summing up the first, the second, and the third value again, we just take the running sum. We've already summed up the first and the second value, and we just add the third value to it. And clearly, when we get to the end, then instead of recomputing the sum of the first 6 elements, we just take the running sum and add the 7th element to it. Much faster. This is why this algorithm also works. And when we look at the number of primitive operations, not determining them exactly, but just the order, we have that one loop, roughly n times. And every statement inside of that loop has to be executed roughly n times. So we have in the order of linear operations here, linear operations in that line here, and that constant operation here. So that gives us 3 times on plus o1, which is obviously on, and just linear. What does that mean in practice? We can look at an implementation, an actual implementation of these two algorithms. Let me get rid of this. This is the prefix averages. Just to demonstrate what happens, I do run this algorithm a few times with increased input size. 3 different runs. The maximum input size that I have here, what is this? 100,000. Then I'm declaring the prototype of these two functions, prefix averages 1 and prefix averages 2, which are defined after the main program. And then I'm running the first algorithm first. It computes the prefix averages here, and everything around it is using some C functions that take the actual clock of my central processing unit and then takes the end time, subtracts the start time, divides this by a constant that is defined in one of the libraries that I'm loading here, the times library, which tells me the clocks per second. And that gives me a rough idea of how much time the processor spent on exactly that particular problem to get from here to here. You don't have to learn this, but if you're interested in actually in measuring the actual processor time that one of your algorithms uses, then you can use a similar program. So I do that with the prefix averages 1 first, and down here I do that with prefix averages 2. Now these two are just the two algorithms that we just saw. This is the slow algorithm, or at least we think that it would be slow because it's quadratic. And prefix averages 2 is the faster algorithm, which has only one for loop. And you can see here that it really is very, very straightforward to take a pseudocode description like this one on the slide and translate it into C. What I haven't done is I haven't initialized the arrays X, because it doesn't really matter what numbers are in there. If I just want to compute the averages, then I can just use whatever it has been initialized, which I, of course, normally shouldn't do. Let me just call it P, and it's called prefix averages. And now let's see. I'm running it with, what were the numbers? With an input of size 1,000, then 10,000, and then 100,000. First, the slow algorithm. So that is very quick for 1,000. For 10,000, it takes a little less than 0.2 seconds. How long will it take for, what do you predict, for 10 times that input? 20 seconds? 18 seconds. Yes, this is exactly what you would expect. If we increase the input size by a factor of 10, then in a quadratic algorithm, it should take 100 times longer to execute that algorithm. And we can see that. It really is very roughly 100 times slower. Whereas the fast algorithm, you can't really see it with these very, very small numbers. But roughly you can see it in particular here, that this really is linear. If you take that time and the input size has increased by a factor of 10, then the running time has also increased by a factor of 10. So not only is the second algorithm much faster to begin with, but it also has a much, much nicer asymptotic runtime behavior. And the result for the runtimes that we see here is really what we should have expected after we did that theoretical analysis. Let's have a look at another example. So that was a difference between quadratic and linear. Here is an algorithm known as binary search, which uses recursion to search for a value in a sorted array. If an array is unsorted, then you have no choice. You have to start from left to right or just start in any order. But in the worst case, you really have to compare every element to the element that you're looking for. Whereas in a sorted array, you can apply what is known as binary search. And that is much, much faster than standard linear search. What it does here is this algorithm searches for a particular value in an array A, restricted to the range from low to high. The output should be true if the value is in the array between low and high, and false otherwise. The way you would call this algorithm is with low to be 0 and high the largest index of that array. That would be the original call to that function. And then what that function recursively does is it computes roughly the middle of the array. It says that if the low is actually greater than high, then you can't find the array, the element within that boundary low to high, because that would be empty. And as a matter of fact, it would have made more sense to put that as the first statement rather than computing the mid first before doing that check, but it doesn't really make a difference. Then if you happen to find the element v right in the middle of the boundaries low to high, you can return true. You found the element. If the element in the middle is smaller than v, then you recursively search in the upper half of the boundaries where you're looking for the element. That's what we have here. And if your element is not greater than the middle element, it's actually smaller than the middle element because it's also not the same. And then you're searching in the lower half of the search space that you're looking for that element. Let's see how that actually works. Suppose you have that sorted array and you're looking for value 8. Now, knowing that the array is sorted, you don't have to go from left to right. You can compute the middle element, which in this case, well, depending on how we implement this, would either be this element or this. Let's say we round down, and then we see that the element that we are looking for, 8, is greater than 5. So we know we can ignore the first half of that array and focus our search in the second half. Then the middle array, or the middle element in that remaining part, is actually this one here. And we find that element immediately and return true. And that was faster than if we had searched just from left to right. Let's look at an unsuccessful search. Suppose we're looking for 7. As you can see, 7 doesn't occur in that array. We start with the middle element 5. 7 is greater than 5, so we are looking in that second half. The middle element here is 8. 7 is now smaller than 8. So we are looking in that very reduced array. Low and high have the same index 3. If that is the case, then the middle element is obviously that element itself. We see that 7 is greater than 6, so we would have to search in the second half of that remaining search space, but that obviously is empty. If we have only that one low to high element here, then we actually end up with low being larger than high, and we had that if condition that if we have reduced our search window to an empty one, then the result is failure. And again, that is faster than going through all the elements and in the end deciding that we can't find the element. If we do a cost analysis of that algorithm, then let me say that all we want to measure is the number of calls to that search procedure for an array of a length I. And this is what I call Ci. Now, for the best case, if we have n elements, we have only one call to that search procedure. What is the best case? The best case is the element we are looking for is right in the middle. And we call our search, we jump to the middle element, and we find our element immediately. Very good, very easy. If we have an array search window from I to j, and j is actually smaller than I, so our search window is empty, then we don't have any recursive call. We had that condition that said we can jump back immediately with false. So if we have 0 elements in our search window, there's no cost because there's no recursive call to search. And if we have an array from I to j with low being smaller or equal to j, then how many calls to search do we have to take? Well, we have to put in one call, and then we reduce the size of the search window by a factor of 0.5. That is, we divide our array either into the left half or the right half. So with every recursive call, we have only n divided by 2 number of elements in our search window. So our recursive call then has an input size of n divided by 2. And no matter how many calls we need in order to find the element here, this is what is required plus 1 to search for an element in an array of size n. And if you look at this recursive equation, it has a simple solution, namely the logarithm to base 2 of n. So you see that C16, for example, requires 1 plus C8. And C8 requires another call plus C4. C4 is 1 plus C2. And ultimately, you get the logarithm, which is, if we start with 16, 4 calls. So binary search is O log 2n, or as we can simply say, O log n. And why is that the case? If you look at the mathematical definition of that O notation, then it is a fairly straightforward and easy proof to show that log 2n to the base 2 is the same as log 3n, is the same as O log 4n, because all these functions are bound by constant factors by each other. And that follows fairly straightforwardly from that mathematical definition. Why is that good? Because with a logarithmic algorithm, we can deal with much, much larger input sizes than even with a linear algorithm. The linear growth would be depicted, and this is now not a log scale, it's or not a log scale, but it's just a standard scale. And you can see that it grows very, very slowly. This is why if you have to search, and this is one of the fundamental tasks for in computer science, for many, many applications, you have huge databases, you need efficient search methods. Logarithmic search methods are always the best solution to any of these problems. To finish up that introduction to the use of mathematics, or mathematical analysis, this is typically some of the math that you should all know from high school that comes in handy when we want to prove, for instance, what I just said, that O log 2n is the same as O log 3n, etc. With the help of these equations, such statements can be easily proved. We have some standard statements that relate multiplications and the power exponential functions x to the power of a to the logarithm to a certain base b, as well as the division and multiplication and division inside an expression of a logarithm. Here are some simply arithmetic equations for exponentials, such as a to the power of b plus c is the same as a to the power of b times a to the power of c. Go through them and make sure that you remember them from high school, or that you convince yourself that they must actually be true. Proof techniques, simple proof techniques, are often being used for statements. One simple proof technique was used here when I said that we have that recursive equation. What solution does it have? The answer is log 2n. And it can be easily proved. Some simple summations might come in handy, such as knowing that if you sum up the numbers from 1 to n, this can be computed with the help of the formula n times n minus 1 divided by 2. Also, basic probability is often being used for complexity analysis, but that only if we are interested more in the average case complexity, which we won't be going into detail a lot here, or if we look at randomized algorithms, which we will do at the very end of this course. Let's have a look at one last exercise before I'm going to have another break. Just give me a second. what is the complexity of this algorithm? Now, this algorithm is a solution to the challenge exercise from last week, where the task was to take a linked list and split it into two halves. Now, one way to do this, and I know that at least one of you found the same solution, is to use 2 pointers, a slow pointer and a fast pointer. The slow pointer always advances 1 element. The fast pointer always advances 2 elements, and they then move in locksteps. And that means that the fast pointer is always at element number 2 times the element, or the, well, if you count the elements in the list, 2 times the element number of the first pointer. And then when you have reached the end with the fast pointer, you know that the slow pointer would point to the middle of the list. And this is where you can split the list into 2 halves. Now, if you look at this algorithm, here, not given in C, but in pseudocode, what is the time complexity of this algorithm in terms of the length of the list? Say you have n elements in the list. What's the complexity? On? Does everyone agree? Is it On? Yes, it is On. You have to go through that list. You have these 2 pointers, so it's probably like O2n, but we know that O2n is On. And if you have to go through that list, even if you jump 2 elements ahead with the fast pointer, and you only visit every other element, then the answer might be On divided by 2, but also On divided by 2 is On. So the answer will always be that the complexity is O with regard to the size of the list. And I think that, let's do that exercise before we have the break. What is the complexity of this algorithm? And that is the one that I had earlier today from a previous homework, the binary conversion, where the input is a positive integer. The output is that binary representation of n on a stack. And the way to do this is you create an empty stack. Then, while your number n is greater than 0, you push n modulo 2. You just compute the remainder, whether it's even or odd, onto S. And then you compute n equals n divided by 2. And here I've used that syntax which indicates the floor. If you have an odd number, like 15, then the floor of 15 divided by 2 would just be the result of integer division, namely 7. This is how you can convert a number. You take 15, divide it, find out that it's an odd number, which is 1, and then you push the 1 onto the stack and look then at the number 7, whether this is even or odd. Again, it's odd, so you push another 1 onto the stack. Assuming that creating a stack and pushing an element both are constant operations, and with the implementations that we have, obviously, they don't depend on the size of the stack. What is the complexity of this algorithm in terms of the number n itself? Log n, yes. So every time you loop through that while you go through that while loop, you divide n by 2. So if you start with, let's say, 1024, the logarithm to base 2 is 10, and you need to do that exactly 10 times. So the answer is indeed log n is the complexity of this algorithm. And with this, now I really have the break, and we will restart at 8:25. Okay. The last 30 minutes for tonight. We have seen a few nice algorithms, quadratic, logarithmic, linear, cubic. Matrix multiplication was cubic. We will look at one more example of a problem that is much, much harder, where we actually will see an exponential algorithm. Before we come to that, can I get everyone's attention also for the last 30 minutes? Thanks. Let me mention that there are two relatives of that big O notation. The so-called big omega notation says that Fn is omega Gn if there is a constant c and an integer n0, so that for all n greater or equal to n0, Fn is greater or equal to c times Gn. So it's just the other way around. And big theta is if you have both. F of n is theta g of n if there are constants c prime and c double prime. And again, an integer constant n0, so that for all n from n0 onwards, you have that Fn is bound by c prime gn and c double prime gn. In which case we say that they grow exactly the same way. Now, typically we only use big O. I just wanted to mention big omega and big theta in case you will see them as well. What do they actually mean? Fn is what we have seen OGn if it is less than or equal to Gn. By the definition on the previous slide, Fn is omega Gn if n is greater than or equal to Gn, so just the opposite. And theta Gn if Fn is asymptotically equal to Gn. Now, as I said, since we always only measure the worst case, and also because it sometimes is harder to say whether the worst case can actually occur or whether our function might not ever encounter the worst case, and it might actually be faster than what we have determined when we counted the primitive operations. We cannot always with full confidence say that we know the exact complexity. That is that Fn, the actual runtime, is theta Gn. We can say that the function that we have determined when we counted the worst case primitive operations, that is theta Gn, but maybe we have been too pessimistic and the worst case will never appear. This is why in practice we typically just say Fn OGn, because then we are on the safe side. Even if we have been too pessimistic in counting the worst case, we still know that the statement that we make is true. Our algorithm runs in OGn. Might be faster, but we can be sure that it's not worse. Well, just examples to illustrate this. If we consider the function 0.25 or a quarter times n square, this is omega n square. And now we have to find a constant c and a constant n0 again, so that our actual function is greater or equal to c times n square, not smaller or equal. And clearly we can find constants by just grabbing this constant here and show this. More interesting is that we can show that n square grows at least as fast as n, and actually it grows faster. And we can show this again by finding constants, so that a quarter times n square is greater or equal c times, now we just have n. Here this is very easy, we just take the constant 1, and for all values greater or equal to 2, this will always be greater than just 1 times n, which is n. And from these two statements, we can say that a quarter times n square is theta n square? Well, not from these statements, but from this statement above here, and the fact that we know that this is O n square. If we combine O and omega, then it just means that the two functions grow equally, and we have a case of one function being in theta of the other function. And of course, it would be the other way around. N square is theta a quarter times n square. When we look at different types of problems in computer science, then we sometimes characterize problems as simple problems or hard problems, not algorithms, but problems themselves. We often have problems that have polynomial worst case performance, and by polynomial we mean that we have a polynomial expression such as n square. We have a quadratic algorithm, and we say that a problem is a polynomial problem if we can find such an algorithm. Some problems in computer science, and these are among the hardest problems that we have to deal with, they have exponential worst case performance. For example, they are in O 2 to the power of n, and no one has found an algorithm yet which can improve the performance. Now, these classes are sometimes abbreviated as P, which denotes the class of problems for which an algorithm can compute an answer in polynomial time. So that would be all the problems for which you have an algorithm that runs in polynomial time. Can be squared, can be cubed, but it has to be polynomial. And NP is a class that I have to be a bit careful in what I'm saying. It is not the class for which you don't have a polynomial algorithm, because that's one of the most famous open problems. But NP stands for a class that includes problems for which we currently don't know a polynomial algorithm. And do be aware of what some people seem to think. NP doesn't stand for non-polynomial. It does stand for non-deterministic polynomial time problem. And the definition for what that means requires that theoretical Turing machine, where I'm now finally coming back to Alan Turing, who I mentioned at the very beginning of this course, who invented this Turing machine, and one of the purposes is to define these problem classes. You might have heard of the P equals NP problem, which is probably the most famous unsolved problem in computer science, which means that we still don't know whether, only because we don't know a polynomial algorithm doesn't mean there doesn't exist a polynomial algorithm. It's one of the open questions whether these classes in the end might not indeed be equal. Most people believe they aren't equal, but this hasn't been proved yet. There is a computer science jargon for difficulty. We call problems tractable if they have a polynomial time algorithm. And that means this is a practically solvable problem. It can be used in practice. Sorting is an example. Searching for an element is an obvious example. Matrix multiplication is also an example. Then we have so-called intractable problems for which we don't know a tractable algorithm. And that is practically feasible only for relatively small n, whereas we can sort 1 million or 10 million elements very easily. An intractable problem can not even be solved for 50 or 60 elements, and we will see an example just in a few minutes. Even worse, there are also so-called non-computable problems. These are problems for which it has been mathematically proven that it is impossible to come up with an algorithm. And again, that goes back to the concept of a Turing machine that defines this concept theoretically. Computational complexity theory is what we call in computer science the area that deals with different degrees of this tractability and intractability. And in particular, there are even several classes of intractable problems. Some are more intractable, if that makes sense, than others. I won't go into detail. This would go far beyond this course, but if you're interested more in these questions, then computational complexity theory is what you will be looking at. Let's end today's introduction into the analysis of algorithms with a famous problem that is really, really hard to solve, intractable, and that at the same time introduces the concept of a so-called generate and test algorithm, which is one of the standard approaches to developing algorithms for problems. Generate and test means we are looking at scenarios where it is simple to test whether a given possible solution, a given state, a given number, let's say, is a solution to a problem. And also, it is relatively easy to generate candidates for solutions, new states, preferably likely solutions that would then satisfy this test and tell us that the candidate that we have generated is a solution. If we have a scenario like this, where it's easy to test whether a candidate is a solution to the problem, and also it's easy to generate candidates, then this generate and test strategy can be used. It is necessary that these possible candidates can somehow be generated systematically, so that in the end we can be sure that we've exhausted all possible candidates and we haven't found a solution, so we can say there is none. And also that we can guarantee to find a solution if there exists one. This is what we typically have for generate and test, although if we look at randomized algorithms, which I am planning to do at the very end of this course, then this will not be required. But for the time being, for standard algorithms that don't use randomization, this systematic way of generating candidate solutions is what you need for a generate and test algorithm. Let's look at a very simple example, checking whether an integer n is prime. What you can do if you're given an integer and you want to check whether it's a prime number or not, you can test all possible factors of n, which would be very easily just all the numbers smaller than n that can be possible factors. And if none of these factors pass the test to be a factor of n, then we know n is a prime number. If you want to check that 27 is a prime number, you start with 1, no, not 1, you start with 2 is not a factor, then you have 3, you see 3 is a factor, so 27 is not a prime number. And if you do that with 31, you enumerate all possible candidates of factors between 2 and 30, then you will see that none of them divides 31, and therefore you know that it is a prime number. So generation is really straightforward. You produce a sequence of all the numbers starting from 2 to n minus 1. Actually, we know we can stop a little earlier, but the simplest algorithm would just do this. And testing is also straightforward to check whether a number divides n exactly. So that's a typical generate and test algorithm where you generate candidates, you test them all, and in the end you have a solution to your problem. This is the algorithm in pseudocode. You just generate all possible factors. You check whether a possible factor is actually a factor. If that is the case, then you return false. You don't have a prime number. And if you have exhausted all possible candidates, you know that you can return true. You have a prime number. If we look at the complexity of this algorithm, it is clear that this is linear. The larger the number, the longer it will take to find all or to test all these candidates. As I've said, and as you probably know, this can be optimized. You don't have to check all the numbers between 2 and n minus 1. You can stop a little earlier and just take the square root of n. It looks a bit funny here, but this should be the square root of n. And then the complexity of the algorithm would actually be O square root of n, and not ON. Let's have a look at a much more difficult problem, namely the so-called subset sum problem. The problem to solve here is you're given a subset of numbers, in this case 2, 4, 6, 8, 10, 30 numbers, And the question is, can you make a selection among these numbers so that when you sum up your selection, the result is 1,000? Can you? Can you select numbers among those that they sum up to 1,000? Anyone? So you see, it's really hard to see. Either what you can do is randomly pick some numbers and check whether they sum up to 1,000, or you have to consider all possible combinations of numbers. And there's quite a lot, even with only 30 numbers. The answer is actually yes. I forgot which combination does it. There are dozens of combinations with this, but it really is not easy to see. This is what is known as the subset sum problem. The general problem is you're given n integers, and you have a target sum k.
55, 85, 101, 389, 186, and 7.
Yeah, that's correct. Very good. I'm very impressed. Okay. Yes. Can you find more solutions? As I said, there are several dozens of them. And you have about 10 minutes to find a few more. Okay, so let's, rather than do that by hand, let's see if we can write a program that solves this problem. And we would like to have a general problem that takes n integers and a target sum, like the 1,000 that we have here, and to determine whether there is a subset that adds up to exactly k. Now there is that, this is really a problem where it's relatively obvious that a generate and test approach is what you would come up with. You test possible solutions, and I assume this is what you have done as well. See whether they really add up to k. If you want to do that systematically, you have to, well, this is what we have to do. We have a set of a of n integers, a target sum, and we want to check whether there is a subset. Well, this is the subset here, so that if we take all the elements in that subset, sum them up, whether we obtain k, then we return true, if that is possible, false otherwise. The straightforward generate and test approach would be to just generate all subsets and check whether the sum of all the elements in that subset sum up to k. If that is the case, then we return true. If we have exhausted really each and every subset and we haven't found one that adds up to k, the answer would be false. How many subsets are there of n elements? Factorial? Nope. 2 to the power of n, yes. Which is actually better than factorial. Factorial would be even more. But still 2 to the power of n. If you have 30, what is 2 to the power of 30? I don't know really, but it's a very large number. So there's a large number of subsets that we have to go through. How could we generate systematically all these subsets? We want to produce all subsets of these integers given an array of integers. There is a nice, very geeky computer scientist-y way of doing this. And this would be to represent sets with the help of n bits. So if you have 4 numbers, then you can use 4-bit numbers to encode all possible subsets. So the quadruple 0 would stand for the empty subset. You don't select any number. 0, 0, 1, 1 would correspond to selecting the 3rd and 4th number. And 1, 1, 1, 1 would correspond to selecting all numbers in that subset. So the bit number I represents the ith input number. That is, if it is set to 1, then AI is in the subset. If it is set to 0, then AI is not in the subset. So if our elements are 1, 2, 3, 5, then the number 0, 0, 1, 1 would represent the subset 1, 2. simply because I'm counting from right to left. So this bit would correspond to the element A0. This would correspond to the element A1. Now that gives you a very nice way of generating all subsets. You just use a for loop that starts at 0. You don't select any element, to 1, 1, 1, 1, whatever the number of elements you have. And in this way, you can generate very easily, systematically, all the subsets. And then you have to use the bit notation here to select the elements and see whether they sum up to the target sum. This is what I've done here. I'm running a loop, just a single loop, from 0 to 2 to the power of n minus 1. If I have 4 numbers, then I have to run from 0 to 15, 0, 0, 0, 0 binary, and 1, 1, 1, 1 binary. If I sum up all the elements in my array AI, for which the ith bit of my running variable is set to 1, then I'm selecting exactly those elements in the array that I want to sum up. And if that gives me the number k that I'm looking for, then I found a solution. So this algorithm looks innocent enough, but if we look at if we want to determine the complexity of this algorithm, we have only one loop. But unfortunately, this loop is not running just from 0 to n, but it's running from 0 to 2 to the power of n minus 1, which of course is the same order as 2 to the power of n. And this is why this algorithm is exponential. It has that exponential runtime. And we will see in a minute that even with smaller inputs, that doesn't really work very well. Here's another approach, which is kind of in the same flavor, also generate and test, but doesn't use the bit numbering, but uses a recursive approach, where the function that is being defined and used recursively here says, I'm looking for the elements in A, but only up to index n, and want to see if I can find numbers in that reduced window that add up to some k. There are two possibilities when I consider a larger array of numbers. Either I take the nth value, if I take it the last number in my array, and decide whether I want to take it as part of a solution or not, then there's two possibilities. Either it is part of the solution. What does it mean? If my last element is, let's say, 99, and my target sum is 1000, and I select the 99, then I have to find elements in the reduced set that add up to 901. Because I've selected the 99, I want to achieve 1000, so I have to find other elements in the remaining array that add up to k minus the element that I've just selected. In my example, 1000 minus 99. This is one possibility. The other possibility is to ignore the nth value. The 99 at the end is not part of any solution. Then I have to find numbers that add up to 1000, my original target sum in the remaining array. That gives us a nice recursive solution. The base case would be that my target sum is 0, in which case all the collected elements add up to the sum that I'm looking for. Because target sum 0 is always be solvable by the empty set. I don't need any number. Or the other base case is I don't have any numbers left. And then this is unsolvable if my target sum is greater than 0. So that then gives us this recursive definition, where if my target sum of the recursive call is 0, I can return true, first base case. If I have no numbers left, and my target sum is not 0, I return false. And otherwise, there are two possibilities. Either I grab the last element, and then I subtract this from the target sum and find elements in the remaining window with n minus 1 elements left, or I don't take it, and then my numbers have to add up to k within the array n minus 1. So that works just as well. The problem is that this isn't any better. If we look at the cost of this algorithm, then, and we count the number of calls to subset sum, then for an array of length I, we see that in the best case, we only need one recursive call. And the best case, the way I have written it, would be that all the numbers in the array add up to 1,000. Then I just grab the first number, and with every recursive call, I will be successful. That is very easy, but the problem is that I don't know which of the two disjunctive cases will be the case. And in the worst case, I have to try every combination, every recursive call without, with the number, and every recursive call without the number. And that gives me a runtime analysis that I have to do 2 recursive calls in every recursive call, and the only solution to that is Cn is again exponential. Thus, my second algorithm is also exponential. Now, I don't think I've got time to do that, but if you go to the web page, you can click on programs, and you will see a program called subset sum, which implements this second algorithm, just a straightforward translation of this pseudocode algorithm in C. And there are a few input cases, set 0, set 1, set 2, that I provide, including the one that we have seen in this example with 30 numbers. With 3 or 4 or 5 numbers, it's really very easy, but with 30 numbers, just an input of 30, it's already very difficult. In this case, the answer comes very fast because there are lots of different combinations, but if you were to use an input number that doesn't have a solution, then you will see that even 30 numbers might be taking for your program too long. You certainly can't solve that problem with 100 numbers or more than 100 numbers, and this is why this is one of the really very difficult so-called intractable problems. We actually call this as an NP-complete problem because there are only algorithms with exponential performance are known. And the problem is, with exponential algorithms, if you only add one number to your input, then you double the execution time. So if you increase the input size by 100, that is, instead of using 30 numbers, you use 130 numbers, it will take that much longer to execute. And this is clearly much worse than linear, quadratic, or cubic. On the other hand, if you are able to find a polynomial algorithm for subset sum, then any other NP-complete problem becomes P. And that would mean that by solving just this problem with a polynomial algorithm, you would instantly become famous because you would have solved the P equals NP problem. I can't take any more questions because I promised that I always end on time. I'll do that afterwards. Let me just mention that the main theme for this problem